Welcome to this deep dive concept explainer brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com.
Hello, everyone.
Today we are taking a deep dive into the introduction of Unit 2, electrostatic potential and capacitance. And we promise a clear, exam-safe explanation that will, I think, fundamentally change the way you understand electricity.
That sounds great.
Okay, let's start with something from the real world.
Yeah.
A question you've probably thought about. We see it all the time, right? Birds sitting on these bare, high-voltage power lines. Totally safe.
Yeah. I've always wondered about that. Those wires carry thousands of volts, but the bird is just fine. How is that possible? Is it some kind of perfect insulator?
That's what most people think, but no, it's something else entirely. And this gets to the very heart of Unit 2. The key isn't what the bird is made of. The key is to ask the right question. Is it the absolute electrical height that's dangerous, or is it the difference in electrical height that matters?
Oh, wait. So you're saying the wire might be at, say, 11,000 volts.
Exactly.
But since both of the bird's feet are on that same wire, they're both at 11,000 volts. So the difference is 0.
Precisely. No potential difference. No current flows through the bird's body. It's
Yeah.
as simple as that.
Wow. But a person on the ground.
A person on the ground is at 0 volts, the ground potential. So if they touch that wire, they create a huge 11,000 volt path to the ground.
And that difference drives the fatal current.
That's it. So our mission today is to properly understand this electrical height, which we call potential. But before we can talk about potential, which we denote by V, we have to understand its foundation,
Which would be?
electrostatic potential energy. You have to start there.
Okay, so how do we get this energy in the first place?
Let's think back to class 11. Remember lifting a rock against gravity?
Yes, the work we do is stored as gravitational potential energy.
Perfect. Electrostatics is exactly identical. You
Right.
just replace the mass with a charge and the gravitational force with the Coulomb force.
So if I have a big positive charge just sitting there,
Right, a source charge.
and I try to push another small positive charge towards it, I'm fighting against the repulsion.
You're fighting a very strong repulsion. That work you were doing, that struggle, it doesn't just disappear. It gets stored
As electrostatic potential energy.
in the system, yes.
The analogy of a hill or mountain really helps here. A positive charge creates a sort of electrical mountain.
A great way to put it. Pushing another positive charge towards it is like rolling a boulder up a steep hill. It takes effort, and that effort is stored.
So since it's just like gravity, does that mean the Coulomb force is also a conservative force?
Oh, absolutely. And that is a critical point for your exams. The Coulomb force is conservative.
And that means the path I take doesn't matter, right? Only the start and end points.
You've got it. Whether you push it straight or into big zigzag, the change in potential energy is exactly the same. It's path independent.
Oh.
Now, why do we even bother with this whole energy concept?
I was going to ask that.
It's to solve what I call the vector complexity problem from Unit 1.
Ah, yes. All those directions and angles and components. It was a lot.
A huge amount of work, wasn't it? Force and electric field are vectors. They have magnitude and direction. But energy and potential, they're just simple scalars, numbers. They can be positive or negative, but that's it.
So this whole unit is basically a mathematical simplification.
It's a hugely powerful simplification. We trade complex vector geometry for simple arithmetic.
Okay, I like the sound of that.
For a mental image, just picture an invisible rubber band connecting two positive charges.
Okay.
As you push them closer, you're stretching that band tighter and tighter. That tension, that stored energy, and that's your potential energy, you. Let go, and it snaps back, pushing them apart.
I like that, the stretched rubber band.
So we have a good feel for potential energy, you. Now, let's bridge this to the more practical concept, potential V. Could you read what insert says about the potential energy difference?
Okay, it says, electric potential energy difference between 2 points as the work required to be done by an external force in moving without accelerating charge Q from one point to another.
Stop there. See the catch.
It mentions the charge.
Q? It depends on the charge.
Yeah.
If you use a tiny test charge, you get a small energy U. If you use a big charge, you get a huge U.
I see the problem. The energy value isn't a property of the location. It depends on what charge I'm using to measure it.
And that's not very useful for, say, an engineer who wants to build a circuit, is it?
No, you'd need a standard map.
Exactly. We need to standardize it.
Yeah.
And the way we do that is actually very simple. We just divide the potential energy, U, by the test charge.
Ah, so you're just normalizing it.
You're normalizing it. This new quantity, V equals U divided by Q, is what we call potential. It's the energy per unit charge.
So the Q cancels out, and V only depends on the location itself.
Now you have a property of the electric field at that point in space, the standardized electrical height.
That makes perfect sense.
Good. Now let's look at the formal definition of potential, because it introduces a word that often confuses students. Could you read that one?
Sure. Electrostatic potential at any point is the work done in bringing a unit positive charge without acceleration from infinity to that point. Okay, why infinity? That part always feels a bit abstract. Why not from, say, the floor?
It's a very sharp question. The thing is, the actual absolute value of potential, it doesn't have any real physical meaning.
What do you mean?
What matters, what we can measure, what drives current, is always the potential difference between 2 points. Remember the bird.
Right, the difference was 0.
So for our mathematical models, we need a convenient place to call 0. And since the electric force gets weaker and weaker as you go far away.
It becomes 0 at infinity.
Exactly. So we just agree, by convention, that the potential at infinity is 0. It's our universal ground reference.
So when we say the potential at point P is 20 volts, we really mean it's 20 volts higher than infinity.
You've got it. It's the work done to bring the charge from that 0 point to point P. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now let's make this concrete with a quick example. Let's really understand what a volt is.
Okay.
Let's say it takes 100 joules of work
W is 100 joules.
to bring a 5 coulomb charge from infinity to some point P.
Q is 5 coulombs.
So what is the potential at point P?
Well, potential V is work per charge. So 100 joules divided by 5 coulombs. That's 20.
Well, what?
20 joules per coulomb, which is
20
5.
volts. Perfect. So the electrical height of point P is 20 volts. And what that means is that any 1 coulomb of charge that you place at P will have 20 joules of stored potential energy.
Got it. It's a property of the location now.
Yes. And understanding this push, this voltage, is the foundation for everything in our next unit, current electricity.
Yeah.
Where we see how this pressure makes charges flow. Okay, now for a very important section, the silent killers. These are the common mistakes that cost students marks, even if they know the formulas.
All right, I'm listening.
Misconception number 1 is about potential energy. The wrong idea is that the energy belongs only to the charge you are moving.
Because that's the one we're calculating the work for, I suppose.
That's why students think it. But the correct idea is that potential energy belongs to the system of charges, to the interaction between them.
The interact.
And remember this hook. It takes 2 to tango. You can't have potential energy with just 1 charge. It's always about the energy of a pair or a triplet of interacting charges.
So if I have 3 charges, I need to calculate the energy for the 1-2 pair, the 2-3 pair, and the 1-3 pair, and add them all up, not just for 1 charge.
Exactly right. Always think in pairs. Okay, misconception number 2. This one is very common. It's about how potential falls off with distance.
Right.
The wrong idea is that potential V falls off as 1 by r squared.
Oh, that's an easy mistake to make, because Coulomb's law and the electric field are both 1 over r squared.
That's exactly why people get confused. They just lump them all together.
Right.
But the correct idea is that potential, V, falls off much more slowly. It falls as 1 over r.
Just 1 over r. Why is that?
The technical reason is that V is the integral of the E field with respect to distance. When you integrate 1 by r squared, you get 1 by r.
Okay, mathematically it makes sense.
But physically, it means that the influence of potential, the electrical pressure, reaches much further out into space than the actual force does. The field might be tiny, but the potential can still be significant.
That's a really useful insight. So force and field are 1rr, but potential is 1r.
Remember that, and you'll avoid a lot of trouble.
Yeah.
Now, to make sure all of this sticks for life, a few quick memory anchors.
Okay.
First, for the sequence of concepts, just remember the letters. WUV,
WV.
work done. WB is stored as potential energy, U, which we normalize to get potential, V.
Got it, WV.
Second, a simple voice. Volts are the push. It's the electrical pressure that makes things happen.
Volts are the push. I like that.
And finally, a physical gesture. To remember that potential is a scalar, not a vector. Just push your hands together.
Okay.
The pressure you feel has a magnitude, right? It can be strong or weak, but doesn't have a direction. It's just a pressure. That's potential, a scalar.
That's a good one. No direction, just magnitude.
Right. So to wrap this all up, let's go over the 3 key exam-safe takeaways from today's deep dive. Number 1, the electrostatic force is conservative. This means the work done is path-independent and gets stored as potential energy, U.
Right. Conservative force, stored energy.
Number 2, electrostatic potential, V, is the energy per unit charge. V equals W over Q. It's a scalar property of a location.
Okay, V is the property of a location.
And number 3, the only physically meaningful quantity is the potential difference. The absolute value is arbitrary, and we just conveniently set the 0 point at infinity.
Difference is what matters. Got it.
Excellent. To get maximum marks in 12 CBSE physics, chemistry, and maths, please visit ProfSam.com.
That is P-R-O-F Sam, right?
Yes, ProfSam.com. Thank you for joining us for this deep dive. Now that you know voltage is about difference, not absolute height, think about this. What other areas, maybe in physics or even in daily life, operate on a similar principle of difference? Study hard and keep learning.